Hello everyone. Today, I'll be presenting our research project titled Scaled Conjugate Gradient, using a strong Wolfe line search for portfolio selection. Optimization is a key mathematical tool used to find the best possible solutions to specific problems. Among the many optimization methods, the conjugate gradient, or CG method, stands out due to its efficiency and low memory requirements. The problem statements for this project are: what is the purpose of studying the SCG method under strong Wolfe line search? Which is the best performance for the SCG methods in terms of iteration numbers and central processing unit, CPU time? And how can the SCG method be implemented in portfolio selection? In line with our problem statements, our objectives are to study the SCG method for solving global unconstrained optimization problems, to compute and analyze the performance of the SCG method in terms of the NOI and CPU time in solving global optimization problems, and to implement the SCG method for portfolio selection. For scope of the research, the scaled CG method is simulated and tested to verify the effectiveness and robustness of the method. 20 standard test functions from the CUTE library are chosen for this research. The scaled CG method with the LAMR, AMRI, RMIL, and NMR coefficient for numerical tests to determine the best method. The best scaled CG method is used in portfolio selection. Let's look at the literature review. Optimization is a decision-making tool that involves with finding the maximum or minimum value of a function. Optimization can be either constrained or unconstrained. Our focus here is on the unconstrained case. The general form is min fx, where x element of Rn. It can be solved by using iterative method, which the formula is xk plus 1 equals xk plus alpha k dk. Fx is minimized at each iteration till fxk plus 1 less than fx. In optimization, alpha k represents the step size, which is determined through a line search process. There are two main types of line search: exact line search, where the value of alpha k is computed precisely, and inexact line search, where alpha k is estimated through approximation techniques. This study focuses on the strong Wolfe line search, an improved version of the standard Wolfe line search, which offers a more reliable and efficient way to determine step size and enhance optimization performance. Next, let's talk about DK, which represents the search direction in an optimization algorithm. The choice of search direction is very important, because different search directions lead to different optimization methods, each with its own strengths and performance characteristics. Here are a few well-known optimization methods, each defined by how it selects its search direction. In our study, we specifically use the conjugate gradient, or CG method. The CG method itself comes in several classes, including classical, hybrid, scaled, free term, and parametric variants. For this project, we focus on the scaled conjugate gradient method. Here are some of the well-known coefficients used in conjugate gradient methods, along with their respective formulas. And this is the overall methodology followed in this study. Here, we show the performance profiles based on two metrics: number of iterations and CPU time. From the first graph, which measures speed by iteration count, we observe that the SLAMR method performed best, followed by SAMRI, SRMIL, and SNMR. The second graph confirms this result in terms of CPU time. Again, SLAMR outperformed the others, proving to be the most efficient coefficient. This table quantifies the success rates of the methods across various test problems. SLAMR achieved a 100% success rate, SAMRI about 99%, SRMIL at 91%, and SNMR at 81%. Clearly, SLAMR is the most robust among the methods tested. Then we implemented our best SCG method in a real portfolio selection task. This involves using stock closing prices to estimate returns and build effective investment portfolios. As shown in figure 5.3, we used historical prices of selected stocks, such as 1023.kl and 1155.kl for function approximation. This table shows the closing prices for CIMB and Maybank. In portfolio theory, lower covariance indicates lower risk when combining stocks. Table 5.3 shows the covariance values between stock returns, helping us construct a diversified and less risky portfolio. In conclusion, all of the four SCG methods have been tested under strong Wolfe line search. Based on numerical results, SLAMR is the most robust method, followed by SAMRI, SRMIL, and SNMR methods in terms of CPU time and number of iteration. SLAMR method can be implemented for portfolio selection. At the end, all the research objectives have been fulfilled. For future research, we recommend use larger optimization problems, use scale with other CG coefficients, solving by using the other line search, and use different software to solve the CG method and the application.